In this video, I'm going to give you some tips for solving the ALEKS problem called identifying elements with a similar valence electron configuration. There are two different types of this particular problem on ALEKS. One type of the problem is giving you something that kind of resembles an electron configuration like this, ms2nd10, and it's asking you to identify all of the elements that share this particular pattern in their electron configuration. The other type of this problem is much more generic. So the other type of the problem is going to say something like shade in all the elements that have a partially full D subshell, or shade the elements that have a half full S subshell, something along those lines. I'm going to start by talking about how you would solve this problem, and I am also going to give you information about how to solve the other version of the problem as well. We're going to do this one first, and I'm going to rewrite that over here, ms2nd10. Okay, so first thing that you might notice when you're looking at this, the letters M and N, which usually are not used in electron configuration. It's not super standard notation. It's telling you here that M and N just represent integers, but if the letters M and N are kind of freaking you out, don't worry, you don't even have to pay attention to them at all. You can just pretend like they're not even there. ALEKS is wanting us to shade in all the elements that have an S2D10 electron configuration. Now, before we start working on that, let's just remind ourselves of the different areas of the periodic table and how they correlate to the orbitals or the S, P, and D areas. So we're just going to kind of mark this off. And then don't forget, please don't forget that helium, even though it's on the right-hand side of the periodic table, it is part of the S orbital. It actually kind of belongs over here if we're thinking about electron configuration. So these are the elements we would refer to as the S elements. These are the P elements. These are the D elements. And as we're counting electron configurations, we can just kind of count across the periodic table. So these are the S1s and these are the S2s. These are the P1s, P2s, P3s, P4s. These would be the D1s, D2s, D3s, etc. So if the problem was just asking us to identify all of the elements that had an electron configuration of S2, we would say, here's this column right here, this is our S2 column, and we would highlight these elements right here. Of course, we would remember that helium is over on that side of the periodic table. If the problem was asking us to identify all of the elements that had a configuration of S2, let's say S2P2, we would say here is S2, and then over here is where we get into P1, and this is P2. So these would be all of the elements that have an electron configuration of S2P2. And it would just be these guys that we highlight. We don't want to highlight any of the ones leading up to it. We just specifically want the ones that are ending with that P2. So hopefully you kind of see the pattern here. My problem is asking for the elements that are S2D10. So really what we're focusing on is just the last part. The stuff that comes before it really doesn't matter. We're just focusing on this final piece. We're looking for the D10 elements, and those guys are 6, 7, 8, 9, 10. The D10 elements are going to be these four right here. If you're familiar with using a periodic table to read or determine an electron configuration, like if somebody said, give me the electron configuration of phosphorus, and you know how to read that off of the periodic table, this variation of the problem is probably going to be pretty straightforward for you. Now, I do want to show you one very tricky version of the problem. It's highlighting all of the elements that have an electron configuration of S1D10. That's kind of funky, and it is definitely possible in your general chemistry class that you've never been introduced to a situation like this before, where the S subshell does not completely fill up before the D subshell starts to fill up. So this S1 instead of S2 might be kind of scary for you. If you see that, I do want you to recognize that that is just a total of 11 electrons, and you can absolutely think of that as S2D9, totally. The S1D10 configuration is actually just the same thing as the S2D9. S2D9 is going to be this area, this column right here. This is where our D9 elements are. Even though there isn't actually anything in the S2 spot, these would be the elements that correspond to 11 valence electrons when we're talking about S and D orbitals. And again, if you're looking at this version of the problem, kind of a bummer, most 100 level Gen Chem classes don't cover that particular topic. So hopefully that's enough information to get you through whatever you're looking at if you have this version of the problem. Now, the other version of the problem is much more generic. So the other version of the problem might say something like, highlight all of the elements that have a partially filled S subshell. partially filled. So this column on the periodic table would represent the elements that have a completely full S subshell. This is 1s1, this is 1s2, and s2 is the maximum for an S subshell. So a partially full S subshell would be these elements right here. It's half full. It's not all the way full. ALEKS could also say a half full S subshell, and that would be the same thing, half full. It might say highlight the elements that have a completely full S subshell, and these would be the elements that have that S subshell completely all the way full. It could also say the same thing for the P element, so it could say which are the elements that have a completely full P subshell. Those are going to be the last elements in each row. It could say a partially full P subshell. So a partially full is going to be everything in the P block with the exception of that last column, because that last column is where it's all the way full. And then it could also say a half full P subshell. Remember that there are a total of 6 electrons in the P shell. So a half full P subshell would be the elements that have a P3 electron configuration. And then last but not least, let's talk about the Ds. You could be asked to give a completely full D subshell. Those would be the guys at the very end. A partially full D subshell would be everything except that last set of, except for these guys. And a half full D subshell would be, since there are a total of 10 electrons in the d orbital, a half full D subshell are going to be these guys right here that have D5. Good luck with this problem.